Now we like flux pinning and we like the Meissner effect, but what, we ask, is the difference? Now, in our previous 10 random liquid nitrogen experiments video, we included a demonstration of the Meissner effect, and in our latest one we've included a demonstration of flux pinning. Now, in that first video we got several comments saying, oh, this isn't the Meissner effect, this is flux pinning. Well, no, it was the Meissner effect, but the effect is quite similar to flux pinning, but it's subtly different. So we thought we'd just make this little video to explain the difference. So firstly, definition of a superconductor: it's a material that when you chill it below a certain temperature, it will conduct electricity with zero resistance. It's a simple definition. Now, there are two types of superconductor. There's a type 1 and a type 2. And again, there are subtle differences between the two types, which we won't really go into now. Now, I've got here a sample of type 2 superconductor. This is yttrium barium copper oxide, and this is a small disc of it. Now, the key thing here is that at room temperature, if we take a magnet and a paper clip, by putting the magnet, and this, I'll do this out of sight so I haven't got the camera angle right, by putting the magnet and the paper clip on there, you can see that the magnet is holding the paper clip through the superconductor. So the field lines of that magnet are actually going through the superconductor. Now, that situation changes when we chill the superconductor down to below its critical temperature, so it becomes a superconductor. At that point, it will expel the field lines from that magnet. So we won't be able to pick it up in that situation and repeat this, but if we could, you wouldn't be able to get the paper clip to stick like this. But what we should see instead is if we put the magnet on top of the superconductor, when we reach that critical temperature and the field lines are expelled from the body of the superconductor, the magnet will levitate. But it's quite a weak levitation and it's quite easy to knock the magnet out of position. So let's try that. Right, so here we have our type 2 superconductor ready to have some liquid nitrogen poured on it with the small magnet on top. So as it reaches its critical temperature, you should see the magnet lift off from the surface of the superconductor. And there we go. Now, as I said, it is a weak effect, so you can see the magnet isn't really held in place. There it is. Now, just a small knock will knock that out of place. But that is the Meissner effect, and the characteristic is seeing the magnet actually lift off from the surface of the superconductor. Now, here's our second sample of type 2 superconductor. Now, the difference here is it's the same material, yttrium barium copper oxide, but instead of being a solid disc, this is a very thin layer coated onto some kind of substrate. Now, the difference that makes is that because yttrium barium copper oxide is quite a complex crystal lattice structure, there are likely to be a fair amount of faults in it. Now, the field lines from the magnet can pass through those areas, those faults, where you may actually have missing atoms, if you like, from the actual lattice itself. So the field lines can pass through those areas, through those faults. And when we chill this down to its superconducting temperature, those field lines become trapped in flux tubes in those faults. Now, that is thought to be the explanation behind the difference between the Meissner effect and flux pinning. It is a bit more complicated than that. There's a lot of kind of quantum theory and stuff like that involved, and if you want to find out more, look it up on Wikipedia or something like that. but that is the simple explanation. So now let's see the difference between what we've just seen, the Meissner effect, and flux pinning. Okay, so here's our second sample of type 2 superconductor. Now this has just been pre-chilled a bit to speed things along, and here's our magnet. Now what we're going to do is the same as with the Meissner effect. We're going to start off with the magnet on top of the superconductor, and then we're going to add a bit of liquid nitrogen. Now as the superconductor passes its critical temperature, we should actually see nothing. The magnet should not move because the field lines from the magnet are now trapped inside the superconductor, so the magnet is unable to move. So we should now be able to pick this up, and the superconductor should remain stuck to there. So if we put this here and just let it warm up for a second, you should see the superconductor just drop off the bottom of the magnet. Now it's not frozen or anything like that, it is the magnetic field lines from there trapped inside the superconductor. Okay, now we're going to try something slightly different. We're going to put the superconductor back into the liquid nitrogen, but this time we're going to hold the magnet 3 or 4 or 5 millimeters above the surface of the superconductor as the superconductor cools down. And once it passes its critical temperature and the magnetic field lines get trapped within it, it should hold the magnet in a levitating position. And you should be able to see that this is quite a strong effect. So in goes our superconductor. Let's hold our magnet just above it as it cools down. Okay, right, now if we let go, you can see that the magnet is levitating above the superconductor. Just keep it topped up with a little bit more nitrogen, like so. Now, unlike the Meissner effect, it's hard to knock that magnet off, and in fact you can now pick up this, give it a good old shake, and it won't come off unless of course the superconductor warms up. Now this is because the field lines from that magnet are trapped in the superconductor itself, so they're very hard to remove. So very similar to the Meissner effect, but much stronger and a slightly different mechanism behind it.